Hello everyone, let's take a look at our next problem. A 10-foot chain weighs 25 pounds and hangs from a ceiling. Find the work done in lifting the lower end of the chain to the ceiling so that it's level with the upper end. Okay, so first thing that comes to mind is I should probably draw a diagram for this. Okay, so here's the ceiling. We have a chain which is fixed to one point and is hanging down, and we're said that this is a length of 10 feet, weighs 25 pounds. Find the work done in lifting the lower end of the chain to the ceiling so that it's level with the upper end. So I assume what this means is that we're grabbing hold of this end of the chain and lifting the entire thing and pulling on it so that the chain becomes level, basically becomes flush against the ceiling. No, so, I mean, when it says so that it's level with the upper end, I'm assuming it's referring to the chain that is level with the upper end. I assume it doesn't mean we're just grabbing this point and lifting it straight up so that the bottom point is touching this. I mean, if that's the case, there's more than one way, depending on, we can grab this end and lift it to touch the ceiling at any point between here and 10 feet out. And the amount of energy used in doing this is different depending on where the end point of this chain ends up. So I'm going to interpret it as that it's not actually, it doesn't actually have to be a chain. It could be a solid rod, and we're just pushing on the end of the rod to move it all the way up to the top of the ceiling here. So the key thing that I'm thinking here is, I want to think of every tiny little portion of this chain as being being its own sort of little block of infinitesimal size, which is being moved up by a certain height. And so we're going to need to figure out, for one tiny piece of this chain, what height does it move through, because that'll allow us to figure out how much energy is needed to lift that piece of the chain by a certain amount of height. And then we're just going to add up all of these tiny little incremental pieces of the chain, and really what that's going to be is we're going to have an integral that goes across the length of the chain. Okay, so what I'm going to do is I'll set up like a coordinate system. I'm going to say that x goes in this direction, and the top part of the chain corresponds to x equals 0. And so for some arbitrary value of x, well, actually this is pretty simple. The height that this piece of chain moves upwards is in fact just going to be x. As this chain gets pulled up to here, each point on the chain, if the chain is initially a distance of x away from the origin point of the chain, then the vertical distance that it moves upwards is also just going to be equal to x. Okay, so for one tiny piece of chain, the energy needed to lift it is gravitational constant times the distance that it moves through times the mass of that piece of chain. We're going to take this gravitational constant as being given. X is simply our, x is just going to be a variable that we're integrate over here. And the mass of an infinitesimal piece of this chain is just going to be the density of the chain multiplied by dx. So the density of this chain, I'll introduce some variables here. So d is the density, which in this case is equal to 25 pounds divided by 10 feet. But for the purposes of the calculation, we'll just use a d. I suppose d is pretty bad because we're going to have a dx at some point. Rho is probably more common use for density. So the mass of one infinitesimal piece of the chain is going to be rho times dx. This is, of course, a linear density. And so the total energy to lift is going to be the integral from 0 to capital L, the length of the chain, of gx rho dx. We'll take the constants out of this expression, and we're just left with g rho. I'll do the integration quickly here, L squared over 2. And I mean, I'm not going to bother substituting in the numerical values of these quantities. The important part of the work here is done. So we're assuming the gravitational constant is given. Rho was given in the question, or at least it could be found quite easily from the question. It's 25 pounds divided by 10 feet. L is equal to 10 feet. Oh, so I suppose there is a bit of a simplification here. G, I'll say W is the mass of the chain. So I'm dividing to get the density. It's the mass of the chain divided by L, and then we have L squared divided by 2. And so in total we have G W L over 2. And I suppose that makes sense too. Now that I see this formula, you know, the end point of the chain is lifted the entire distance L. The fixed origin point of the chain doesn't move at all, and every point in between the distance that it moves through, the vertical distance it moves through, is going to be proportional to the distance that it is from the fixed point. And so lifting this chain up so that it is level with the ceiling, the amount of work is no different than moving just the center of mass of the chain up to the top of the ceiling. And so that's where this L over 2 comes from. You know, this amount of energy is the same as if we had a single point mass of mass W, but it's moving through a distance of L over 2. But this just sort of shows that, you know, this simplification works. Now, I suppose the question is open to interpretation, exactly what it means, where it says the lower end of the chain is lifted to the ceiling, so it's level with the upper end. In fact, what I'm going to do is I'm going to make a follow-up video quickly where I take the other interpretation where this bottom point is simply moved directly straight up to the top point, and we'll go through the computation of that in just a second. Okay, this is a follow-up video to a question I solved, which dealt with having a chain hanging from a ceiling and moving the end point of the chain through some distance and computing the amount of energy needed to do that. So in the original video, what I'd said was the chain was hanging here, and depending on how you interpret the exact wording of the question, it said the end point of the chain is lifted so that it is level with the ceiling. Now, when it says it's level with the ceiling, I don't know if they just mean the end point or if they mean the entire chain itself. So in the previous video, I'd solved the amount of energy needed to take this point and raise it to the ceiling over here so that the chain itself becomes level with the ceiling. But I think maybe the question wanted us to interpret this differently, where we take the end point of this chain and we just lift it straight up so that the end point now touches the ceiling, and we should compute the amount of work done there. So the first thing that comes to mind here, the first thing I'd really like to do is set up some kind of coordinate system. And I think what I'll do, this is actually different from what I did in the previous version, or the previous version of the solution. I'm going to say that this bottom point now is x equals 0, and x increases as we move upwards on the chain. And the reason I'm doing this is because I realized very quickly that everywhere from the top of the chain down to the midpoint, is not going to move. This part of the chain is going to be completely stationary, and so it's only this part of the chain down here which ends up moving. And so naturally there's going to be a point on the chain at a distance of L over 2 where we're going to be integrating from x goes to 0, x with a lower limit of 0 up to an upper limit of L over 2 in our integral. And the thing we're going to be integrating is the amount of work it takes to move one small infinitesimal piece of our chain through whatever distance it ends up moving. So what I'd like to do now is figure out how much, I need to figure out what is the vertical distance moved by this infinitesimal piece of chain. So of course, a piece of chain down here is going to end up almost at the top, but a piece of chain that starts very close to the midpoint is going to end also very close to the midpoint, but on the other side. So let's just try and figure out the distance that, that a piece of this chain moves. Okay, so if the position of this piece of chain is x, well, if x is equal to 0, the distance it moves is L. If x is equal to L over 2, the distance it moves is 0. And it's pretty clear that the distance moved by any piece of chain is going to vary linearly as x goes from 0 up to L over 2. So what we want is I want a linear function of x such that when evaluated at 0, I get L, and when evaluated at L over 2, I get 0. Okay, so this distance, I don't want to use the letter d because that'll appear in our differential later. I'll use a distance of, I'll say p is the distance as a function of x. Okay, so we'll have an x minus L over 2, and I suppose we have to multiply this by 2. Okay, so, oh, no, that's not right at all. It should be L over 2 minus x. Okay, so when x is equal to 0, this evaluates to L, meaning that this point moves all the way to the top. When x is equal to L over 2, this evaluates to 0, meaning this point doesn't move at all. And it's linear between those 2 points, and so I know that this is the only function which gives us that. Okay, so the energy needed to lift this one infinitesimal piece of chain by this distance it's just going to be p of x multiplied by the mass of that piece of chain, which is, you know, could in fact be a function of x. It'll actually be a constant in this case, and multiplied by some kind of gravitational constant. So m of x is the thing that we need to figure out. What is the mass of an infinitesimal piece of chain? So this is the same as we had in a previous version of the problem. It's just going to be the density of the chain multiplied by dx, the size or the length of this infinitesimal piece. So rho times dx, where rho is equal to the total mass or weight of the chain divided by the length of the chain. And both of these quantities were given in the statement of the problem originally. All right, so the total energy needed here we just need to take the energy needed for each infinitesimal piece of the chain, and we're going to add these up, but we're adding over a continuum of points here. So this is just going to end up being an integral as x goes from 0 to L over 2, g times p of x times rho dx. We'll factor out the constants. We'll make the substitution for what this function p of x is. It's 2 times L over 2 minus x dx. So I have 2g rho integral from 0 to L over 2 of L over 2 minus x. Can take an antiderivative of this pretty easily. It'll be L over 2 minus x squared. And I suppose we'll have to multiply by negative a half. So I'll just get rid of this 2 and put a negative sign in front. And we need to evaluate these at the two endpoints. So when I evaluate at the first endpoint, I of course get 0, so I won't write that down. And what am I left with? I'll have g times rho times L over 2, which, believe it or not, is the same expression we had when we did this problem with the alternative method. So now I'm wondering if it even matters how we lift this bottom point up to the top. If I took this point and lifted it here, so it's not directly above, it's not directly on top of where the chain is fixed to the ceiling, but it's also not the maximum possible distance away. I wonder if the total work done is independent of that quantity. That's a much more, yeah, see here we have GWL over 2. Oh, I forgot to square something. Maybe these are not the same. Hold on a second. Let me just go through this carefully. What am I doing? Okay, so when I evaluate it at the upper bound, this disappears. So I'm just evaluating at the lower bound. I have g rho L over 2 squared, which is g, and rho is equal to w divided by L, and then I have L squared over 4. Oh, so these are in fact different. Okay. Well, ignore everything I just said. When you lift the bottom point straight up to the ceiling, apparently it takes half as much work as when you lift it, to a point in the ceiling which is away from the fixed origin point by a distance of L. All right, so sort of two different solutions to the same problem depending on how you interpret it. But nice, cute little problem.